The pursuit of artificial intelligence is the effort to simulate human cognitive functions inside a machine, giving a computer the ability to reason, solve problems, and perceive its physical environment. Within that broad pursuit is machine learning. Instead of relying on hard-coded instructions, this subset uses statistical algorithms to make decisions. By feeding these algorithms historical data, the system identifies patterns and improves its own performance, grouping inputs without explicit programming. This approach is highly effective for many applications, but its utility is strictly bounded by the structural complexity of the data you feed it. Defining the exact boundaries between these concepts is a matter of practical engineering. The problem you are trying to solve dictates the mathematical architecture required to process the data. Traditional machine learning algorithms excel when processing structured datasets, like tabular financial records or organized CSV files. Processing this data requires a human-led step called feature extraction. Engineers must manually isolate the relevant variables, such as an applicant's income or credit history, before handing that information to the algorithm. But the physical world rarely provides neatly organized spreadsheets. Images, audio streams, and natural language represent unstructured data, where variables are buried within chaotic environments. A human engineer cannot manually isolate and write a mathematical definition for a pedestrian or a traffic light from a raw array of millions of shifting pixels. This limitation in handling dense, unstructured inputs forces a shift in architecture toward deep learning. By utilizing multi-layered neural networks, the system moves past human-guided feature selection and begins performing automated mathematical feature discovery on its own. If a hospital wants to predict patient risk, a traditional statistical algorithm can easily process a structured database of ages, blood pressures, and existing conditions. That same algorithm cannot evaluate a high-resolution X-ray or MRI scan to locate a medical anomaly. A tumor does not exist as a discrete numerical column. It is a complex spatial pattern composed of subtle variations in pixel intensity across a visual matrix. Deep learning bypasses the need for manual feature extraction by deploying artificial neural networks that ingest and interpret the raw pixel matrix directly. The mathematical architecture of deep networks provides the specific capacity to perceive patterns in data too dense and disorganized for traditional statistics to process. The foundational computational unit of these networks is the single artificial neuron, derived from the Macaulay-Pitts model. Processing begins with an input vector, representing the raw data flowing into the node, such as individual pixel values from an image. Inside the node, each input is multiplied by a specific weight, and an additional value called a bias is added. These parameters determine how much importance the network assigns to each incoming piece of data. Simply summing these weighted inputs results in a linear transformation. If the network stopped there, it would be incapable of mapping the complex realities of the physical world. To solve this, the node passes its final sum through an activation function. This mathematical threshold introduces non-linearity to the output. Without activation functions, the entire architecture of a multi-layered deep neural network would mathematically collapse into a basic, single-layer linear regression model. This chart illustrates the sigmoid activation function. Historically, engineers used this formula to compress network outputs into a strict probability range between 0 and 1. Looking at the derivative graph on the right, the curve peaks at 0.25 and quickly tapers off towards 0 at the extremes. During the backward propagation of errors, this causes the learning process to stall, a limitation known as the vanishing gradient problem. To maintain gradient flow in deep architectures, modern networks typically use the rectified linear unit, or ReLU. ReLU simply outputs the maximum of 0 or the input value. By returning a constant gradient of 1 for all positive inputs, it prevents the gradient from vanishing and enables highly efficient weight updating. However, this efficiency introduces a specific vulnerability. If a negative input causes the derivative to drop to 0, the neuron dies and permanently stops updating its weights. Despite the risk of dead neurons, the system utilizes backpropagation, applying the chain rule of calculus to continuously calculate errors and adjust the network's internal parameters. The precise mathematical function selected for these nodes dictates whether a network successfully maps high-dimensional data or mathematically stalls out during the training phase. When millions of these individual nodes are stacked into a complete deep neural network, the input layer passes raw data into a sequence of hidden layers. The first hidden layer processes the raw pixels to isolate basic structural edges and gradients. The second layer takes those isolated edges and combines them to identify complex shapes and distinct visual textures. The deepest layers synthesize these shapes into the recognizable, abstract form of a tumor before reaching the output node. This process is called hierarchical abstraction. It requires no human intervention. It occurs entirely automatically as the network uses backpropagation to optimize its own weights. By stacking layers of non-linear transformations, deep learning successfully parses the unstructured data that paralyzes traditional statistical models. Moving from mathematical theory to real-world deployment reveals a steep hardware cost. Traditional machine learning algorithms execute efficiently on standard CPUs, but deep networks demand a vastly different physical architecture. Training a deep model requires processing millions or sometimes billions of parameters simultaneously. This level of parallel computation specifically requires graphics processing units, or tensor processing units. Alongside specialized processors, deep networks must ingest massive volumes of labeled, unstructured data across thousands of training cycles before their weights accurately converge. While this architecture offers superhuman perception, the extreme dependency on high-performance compute clusters and massive datasets creates a severe barrier to entry compared to traditional structured learning models. Beyond hardware costs, the architecture introduces a critical structural limitation, a severe lack of model interpretability. When a traditional algorithm like a decision tree denies a bank loan, a human auditor can trace the logic step by step and identify exactly which variable triggered the rejection. In a deep neural network, features are extracted automatically across millions of hidden parameters. The specific logic path the network uses to reach its conclusion is obscured from human operators. This creates the so-called black box problem. The inability to explain an AI's decision-making process becomes a critical liability when deploying these systems into high-stakes environments like medicine, law, and autonomous driving. The taxonomy of computational intelligence is clear. Artificial intelligence provides the overarching goal. Machine learning supplies the statistical tools to evaluate structured data, and deep learning provides the neural architecture required to perceive the unstructured world. Advancing the field requires a departure from simple hardware scaling.
Hey everyone, and welcome to this explainer. Today we're going to break down three massive buzzwords: AI, machine learning, and deep learning. We hear these terms literally all the time, right? But how exactly do they fit together to solve actual complex human problems? Well, we are going to unpack exactly how these technologies process information and, more importantly, how they are completely reshaping the world around us. Let's get into it. So here's our roadmap for this explainer. We'll start with the intelligence nesting doll, move into machine learning, dive deeper into deep learning and neural networks, talk about mastering complex, unstructured data, and wrap up with how this solves real human problems. All right, let's kick things off with Section 1, the intelligence nesting doll, unpacking the layers of intelligent computing. Now, we often hear terms like AI and deep learning tossed around interchangeably, like they mean the exact same thing, but honestly, the best way to picture this is like a set of Russian nesting dolls. The largest, outermost doll, that's artificial intelligence. This is a super broad field that really represents the ultimate goal of computer science, creating systems that can actually mimic human cognition. And that includes everything from basic, old-school, rule-based systems that just follow simple if-this-then-that logic, all the way up to the highly advanced, data-driven stuff we're going to look at next. It's essentially the giant umbrella over things like robotics, natural language processing, and a whole lot more.
Moving right along to Section 2, machine learning, finding patterns.
So we pop open that big AI doll, and what's inside? Machine learning. And the shift here is pretty profound. Instead of us, humans, writing fixed, rigid rules for a computer to follow, the machine actually analyzes past data to make predictions in totally new situations. It's learning and improving with experience, just by finding patterns in whatever historical data we feed it.
But here's the absolutely crucial point about how traditional machine learning works. It loves structured data. Think neat little rows and columns in a spreadsheet. But there's a catch, and it's a big one. It requires manual feature extraction. That means human experts actually have to step in and hold the algorithm's hand, telling it exactly what to look for. Say you want to predict a Zillow home value. A human has to manually identify that square footage, the number of bedrooms, and the location are the key features. Or if you're building a spam filter, a human has to flag the specific spammy words. It absolutely needs our guidance to work.
Which naturally brings us to a major hurdle. What happens when the real world gets messy? Traditional machine learning struggles heavily with raw, complex, unstructured data. Think about a raw audio clip, a massive video file, or a complex medical X-ray. A human expert literally cannot sit there and manually extract every single pixel or sound wave as a feature. It's just impossible. And that brings us to Section 3, Deep Learning and Neural Networks, the innermost nesting doll. To solve that massive problem of messy data, we pull out the innermost, most complex doll of the bunch, deep learning. This is where the whole system begins to learn automatically, with basically zero human guidance. Deep learning is heavily inspired by the human brain, using things called artificial neural networks. By stacking many layers of these artificial neurons, the system can automatically extract its own features directly from raw data, entirely bypassing the need for a human to organize it first. It's honestly a real game changer. So here's the huge contrast between our middle and inner nesting dolls. While machine learning needs a human to extract features for it, deep learning acts like an absolute powerhouse, figuring out all those complex features completely on its own. Because this takes a massive amount of computing, deep learning relies on incredibly powerful GPUs, rather than standard CPUs, to process billions of parameters. But of course, there's a trade-off. While traditional ML is pretty easy for us to interpret, deep learning often acts like a black box. It's kind of hard to see exactly how it arrived at its final conclusion. Let's move into Section 4, Mastering Complex Unstructured Data. We're going to look inside the neural network. Let's actually look under the hood at the architecture that makes this so insanely powerful. You can think of a neural network as an automated assembly line. First up, the input layer receives the raw data, let's say millions of individual pixels from a single image. Then that data flows into the hidden layers. And guys, this is where the magic happens. Through a whole series of weighted connections and nonlinear math, these intermediate layers automatically extract increasingly complex features. First, it might find basic edges, then it spots shapes, and eventually it recognizes full objects. Finally, the output layer delivers the final prediction. No human feature engineering required whatsoever. Now, this next part absolutely blows my mind. How does the network actually learn? Well, it uses two main processes. In a feed-forward pass, data flows strictly in one direction, from input to output to make a guess. But the actual learning happens during backpropagation. The network looks at its output, calculates how far off it was from the right answer, and then literally reverses the flow of information backward through the layers. It calculates the errors and adjusts the weights of every single connection, correcting itself so it doesn't make that same mistake next time. But remember that black box dilemma we mentioned earlier? Because these hidden layers are creating their own highly complex mathematical representations, sometimes over dozens or even hundreds of layers, the exact reasoning behind a deep learning model's output remains a bit mysterious to us. We know for a fact that it works, and it often achieves way higher accuracy than human experts, but explaining exactly why it made a specific prediction, that's still incredibly difficult. All right, finally, Section 5, Solving Real Human Problems, taking this from abstract math to tangible impact. We've been zoomed way into the microscopic math, right? So let's zoom back out. How are these neural networks actually changing our day-to-day world? By automatically extracting features from messy, raw data, deep learning is providing massive, literally life-changing solutions across every major industry. In healthcare, convolutional neural networks, or CNNs, are analyzing complex scans to save lives. In transportation, real-time object detection is making autonomous self-driving cars a reality. And in finance, these models are monitoring millions of rapid-fire transactions to instantly block credit card fraud before it happens. Let's take a closer look at healthcare for a second. The sheer ability to feed raw, highly detailed medical images straight into an input layer, and then have those hidden layers automatically flag an anomaly, is completely revolutionizing early diagnosis. The sources for this explainer highlight projects using CNNs to detect breast cancer from super complex imaging, classify lung cancer, and spot pneumonia using chest x-rays. These networks are predicting disease risks and spotting tiny visual patterns much earlier than the human eye ever could.
It's amazing. And it's the exact same story for self-driving cars. They rely entirely on deep learning to navigate safely. Think about it. The physical world is chaotic and totally unstructured. A vehicle has to instantly process a constant, massive stream of data coming in from cameras, radar, and LiDAR sensors. Deep learning models are what classify a pedestrian versus a stationary mailbox in real time. They plan safe routes instantly, and they adapt on the fly to visual disruptions like fog, rain, or snow, totally without human intervention. Honestly, these applications powerfully illustrate the point made in this quote from our source material. These technologies aren't just abstract mathematical concepts running quietly on some GPU somewhere. They represent a fundamental leap in how we solve our most daunting challenges as a species. By mastering data that was previously just way too vast or messy for us to comprehend, machines are now beginning to surpass human capabilities in some really critical domains. From the big, broad ambition of artificial intelligence down to the statistical patterns of machine learning and right into the hidden layers of neural networks, we've really unpacked the tools that are building our future today. Thank you so much for joining me on this explainer. And before we go, I want to leave you with this to think about. As we keep pushing the boundaries of these automated feature extractors, what impossible human problem do you think the next iteration of intelligent computing is going to solve? Welcome back, everyone, to today's explainer. You know, we hear so much about AI models these days, models that can perfectly recognize faces, flawlessly translate languages, or literally drive cars. But beneath all that flashy magic, there's actually a surprisingly simple foundational piece of math running the whole show. Today, we're setting the stage to uncover the exact mathematical engines that allow deep learning to actually work. It's the ultimate question, isn't it? What actually makes a neural network learn? I mean, we know we feed data into an input layer, it passes through some hidden layers, and boom, it spits out an output. But what is that actual spark? What transforms that raw data from just, simple numbers into complex understanding? Well, let's dive into this and look under the hood at the real mechanics of an artificial neuron.
And here is our answer, the activation function. Basically, this is a mathematical operation applied to a neural network node's output to determine whether it should be activated. Should it pass its information forward or not? Without the specific step, our incredibly complex AI models, they'd just be basic superlimited linear calculators. They'd just be multiplying weights and adding biases over and over and over. They would absolutely never be able to learn the messy complexities of the real world. To really wrap our heads around this, think about a biological neuron in the human brain. A brain cell receives signals through its dendrites, right? And if that total accumulated signal is strong enough, it fires an electrical impulse straight down the axon. Well, an artificial node perfectly mirrors this exact firing mechanism. It receives inputs, sums them all up, and then the activation function steps in as the ultimate gatekeeper. It essentially asks, okay, do we fire and pass this signal on? So the absolute secret sauce here is non-linearity. By introducing non-linearity, we give the neural network the superpower to bend, twist, and mold its understanding to fit complex, real-world patterns instead of just drawing rigid, straight lines. Because let's face it, the real world is not built out of straight lines. Well, unless you live in Minecraft. Whether it's the subtle curve of a handwritten letter or the unique frequencies of human speech, non-linearity is the exact property that makes learning those things possible. Section 1. First-generation heroes, Sigmoid and Tanh. Let's travel back a bit chronologically and check out the earliest mathematical functions developers used to introduce this crucial nonlinear spark. Comparing these two side by side reveals some really fascinating trade-offs. First up, we've got the sigmoid function. It takes literally any input and squashes it into a tight range between exactly 0 and 1. Because of that, it's brilliant for outputting a probability. That makes it the absolute go-to for binary classification tasks. Output layer stuff, like deciding, is this a cat? Yes or no. Then we have Tanh, or the hyperbolic tangent. It's kind of similar, but it maps inputs between -1 and 1. Because it's zero-centered, it typically leads to much more efficient weight updates and faster convergence when you use it in the hidden layers. But as researchers started building deeper and deeper networks, a devastating villain emerged. They kept hitting this invisible wall, realizing that at a certain depth, the network simply stops learning. The training progress would just completely flatline. No way around it. And that brings us to the dreaded vanishing gradient problem. So during learning, networks use backpropagation to update their weights, moving backward from the output. Think of it like playing a giant game of telephone. Because functions like Sigmoid and Tanh heavily squash large values into tiny little ranges, the message, or the gradient, shrinks exponentially as it gets passed backward layer by layer. By the time that signal finally reaches the early layers, the gradient effectively vanishes to practically nothing. Those early neurons receive basically zero learning signal, so they just stop updating altogether.
Section 2, the modern savior, the ReLU revolution. The deep learning community desperately needed a massive breakthrough if networks were ever going to scale up. Enter the rectified linear unit, or ReLU, and the genius of ReLU lies in its breathtaking simplicity. The rule is basically this. If the input is positive, the function just outputs that exact same positive number. But if the input is negative, the output is simply a massive 0. That is it, just 0. It is incredibly fast to calculate, and most importantly, because the positive side doesn't squash the values down, the gradients don't vanish. That crucial learning signal can flow backward through dozens, even hundreds of layers without shrinking.
However, even heroes have a tragic flaw, right? And ReLU's Achilles heel is what we call the dead neuron problem. See, because ReLU outputs exactly 0 for literally any negative input, if a large weight update causes a neuron to consistently output negative numbers, the gradient becomes 0, period. And when the gradient is 0, the weights can't update anymore. That neuron just gets permanently stuck. It stops processing information, it stops learning, and it effectively dies. Just game over for that node.
So let's trace the mathematical evolution built specifically to fix that dead neuron issue. Step 1 was our base ReLU. Amazing speed, but yeah, neurons die. So researchers cleverly whipped up step 2, leaky and parametric ReLU. Instead of a flat, hard 0 for negatives, they introduce a tiny little slope or even a learnable parameter. This ensures the gradient never truly hits 0, effectively resurrecting those dead neurons. Pretty cool, right? Then step 3 introduces ELU, the exponential linear unit. This one uses a smooth exponential curve for negative values. It keeps things nicely zero-centered and highly accurate, though, fair warning, it is slightly more computationally intensive to process.
Moving on to our final section, modern specialized activation functions. Because as deep learning has expanded into massive new domains, the basic functions just aren't always enough. A perfect example of this specialization is the softmax function. You can think of softmax as the ultimate, supercharged extension of the sigmoid function. While sigmoid is great for a simple binary choice, softmax is built specifically for the output layer of complex, multi-class problems. So if your AI needs to look at an image and decide, hey, is this a dog, a cat, a car, or a tree? Softmax takes all those raw scores from the preceding layer and normalizes them. It creates this perfect probability distribution across all the classes, guaranteeing that the total sum of all those probabilities equals exactly 1, or, 100%.
And beyond the output layer, deep inside the hidden layers of the most massive models today, like transformers, we're seeing some incredibly advanced functions. Take ReLU, for instance. It intelligently adjusts inputs based on their probability within a Gaussian distribution. Then there's Switch. Swish is the specialized, smooth activation function actually discovered through automated search techniques, and it occasionally outperforms ReLU in really deep networks. It's honestly just fascinating to see how highly specific and mathematically complex these tools have become to power modern AI.
We've seen how a surprisingly simple mathematical decision, basically to fire or not to fire, evolved. It went from the foundational Sigmoid to the lightning-fast ReLU, all the way to highly specialized tools like ReLU and softmax. But math never stops evolving. As AI architectures grow to trillions of parameters, what new activation function will spark the next revolution in learning? It's something to think about. Keep exploring, keep learning, and thank you so much for joining me in this explainer.